Hello guys. Today we will examine 5 codes that I have prepared in Java. First of all, um, the code defines a function called partial sum of squares that takes an array of integers r and an integer n as parameters. Here's a breakdown of how it works. It starts by initializing variable result to 0. This variable is used to accumulate the sum of certain values, and the function includes a for loop that iterates from 0 to n subtraction 1, and for each index I, it checks if the value at that index in the array ri is negative, and inside the loop there is an if statement that checks if the current element of the array is less than 0. If the condition is true, it adds the product of ri and itself to the result. After completing the loop, the function returns the final value of result. Let's continue. Let's run. The output, for example, 5, and the output is 25. Let's continue. Second code. The image contains several code fragments, each followed by a question about their time complexities. Let's break down the time complexities of each fragment in a conversational way. This loop runs from 0 to n power of 2, performing a simple operation in each iteration. Since the loop iterates n squared 2 times, the overall time complexity is O n squared. And for here the loop increments e by 44 every iteration, so it runs approximately and division 40 times, which simplifies to O(n) since constant factors are ignored in big O notation. O(n), this loop increments e by n each time because it runs from 0 to n power of 2. The total number of iteration is n power of 2 division n, which simplifies to O n. The loop begins at 10 and runs until approximately n of 2 division 3, incrementing by 2 each time. The number of iterations is Rowley m power of 2 division 6, which is still O m power of 2 when considering big O notation. This loop runs a constant number of times, which means its time complexity is independent of any variable input size. Thus, it is O1. Let's continue. This loop starts at 1 and doubles each iteration. It continues until A exits, and the number of iterations required is logarithmic in relation to n, so the time complexity is O log n. Time complexity O1 is similar to the previous case. If n starts larger than 10, this loop will run a constant number of times before exiting, so its complexity can also be considered O1. The complexity O n multiplication m. The outer loop runs approximately n division 100 times, and the inner loops run m subtraction 40 division 4 times. The total time complexity becomes O(n) multiplication m. Time complexity O(n) multiplication m. Here the outer loop iterates logarithmically with n, but since the inner loops run m division 2 times for every outer iteration, the overall complexity remains O(n) multiplication m. Let's run the code. Look, output is 5. Let's continue. Function definition. The function recursive power, and it takes two parameters, x, which is the base, and n, which is the exponent. If n is 0, the function returns 1. This is because any number raised to the power of 0 is 1. If n is 1, the function returns x. This means that any number raised to the power of 1 is the number itself. If n is even, the function calls itself recursively with parameters x multiplication x and n division 2. This effectively reduced the problem size by half. If n is not even, the function calls itself recursively with x multiplication x again, but it uses n division 2 and multiplies the results by x. It handles the case where you have an odd exponent by using the formula x power of n where x power of n subtraction 1 multiplication x. The recursive power function has a complexity of O log n. Here's why. Each time the function is called with an even n, the size of the problem is out because of the n division 2 operation. And for odd n, the function still effectively halves the size in the recursive call, even though it involves one additional multiplication. Let's run. So In summary, this function efficiently calculates x power of n using recursion, applying the principle of exponentiation by squaring, which allows it to achieve a time complexity of O log n. And let's continue. Recursive fib again. The function is named recursive fib, and it takes one integer parameter n. And base case, the first line checks if n is less than or equal to 2. If so, the function returns 1. This is because the first two Fibonacci numbers, f1 and f2, are both defined to be 1. If n is greater than 2, the function makes two recursive calls. Recursive fib n subtraction 1, which calculates the n subtract 1, the Fibonacci number. Recursive fib n subtraction 2, which calculates the n subtraction 2, the Fibonacci number. The function then returns the sum of these two calls to match the definition of Fibonacci sequence. And each call to recursive fib generates two additional calls, creating a binary tree of function calls. For example, to compute fn, you need to compute f n subtraction 1 and fn subtraction 2, and this pattern continues, leading to an exponential growth in the number of calls. The depth of this recursion can go up to n, and the branching factor is 2, resulting in a total time complexity of O to power of n. In summary, let's run. The recursive fib function calculates the nth Fibonacci number using a straightforward recursive approach. However, due to the nature of its recursive calls, it has a time complexity of O to power of n, making it inefficient for large values of n, as it lets a lot of repeated calculations. A more efficient approach would involve using dynamic programming or memoization to store previously calculated Fibonacci numbers. And last code, let's look this portion, fast versus slow computer algorithm. You have a fast computer that is 10 times faster than a slow computer. Algorithms is fast algorithm runs as on O1 time. This means that as the size of the input n increases, the time taken grows linearly. Slow algorithm. This algorithm runs in O n power of 2 time. This means the time taken grows quadratically as the input size increases, making it much slower for larger inputs. So if n is relatively small, the fast algorithm running on the slow computer could be faster. If n becomes large enough, The slow algorithm on the fast computer will likely become faster because the linear growth of the fast algorithm will eventually be outpaced by the quadratic growth. Thanks for watching.